Welcome back to the deep dive. I want you to think about something for a second. Think about your morning routine today.
Yeah, the stuff we just do on autopilot.
Exactly. You woke up, maybe hit snooze on your phone's alarm clock. You went to the kitchen, grabbed a box of cereal, and, well, maybe you glanced at the barcode on the back while you pour the milk.
Right.
Then you hopped on your phone, opened your banking app to check your balance, and started streaming a playlist to get your day going.
Pretty standard morning for most of us.
Right. And the alarm clock, the barcode, the secure connection to your bank, even the length and structure of the songs you listen to, they all seem completely unrelated, right? Just random, disparate parts of modern life.
Yeah, totally unconnected.
But what if I told you that beneath the surface of every single one of those interactions, there is a hidden engine, a very specific, highly structured type of invisible math running the entire show?
It really is running the show.
Today, we are opening up a massive stack of research and field applications from a document called Modular Arithmetic and Applications. And honestly, once we peel back this layer of reality, it is going to completely change how you view your daily life. You're going to start seeing the matrix everywhere.
It genuinely is a profound shift in perspective.
Oh, yeah.
Most of us go through our day assuming that the digital and physical systems we interact with are either completely chaotic or governed by, impossibly complex, inaccessible computer code.
Right, like magic we can't understand.
Exactly. But when you look at the underlying architecture, it always boils down to an incredibly elegant set of mathematical rules.
Well, and our mission for this deep dive is to demystify those rules. We are taking modular arithmetic out of the dusty realm of, abstract theoretical mathematics. We're going to show you exactly how it builds digital trust, organizes global data, and even dictates the emotional impact of the music you listen to.
It touches literally everything.
Okay, let's unpack this right out of the gate. Because as I was combing through the foundational concepts in the research, I found myself trying to visualize how this is actually different from the math we all learned in grade school.
It takes a minute to wrap your head around, for sure.
So picture traditional math as an infinite highway. It just stretches forever in both directions. You start at 0, you add numbers, and you just keep driving forward into infinity.
Right.
You subtract, you throw the car in reverse, and you drive backward into negative infinity. There is no end. But modular arithmetic, well, it's not an infinite highway. It feels more like a closed racetrack.
That is a really solid way to visualize it, because the fundamental difference is that in this system, the number line is finite. It's a closed loop.
A loop.
And the size of that track, the formal concept that defines the absolute boundary of the system, is called the modulus. Mathematicians usually represent it with a lowercase letter m.
So the modulus is basically the finish line. But the moment you cross it, you're instantly back at the starting line.
Precisely. Given any positive integer m that is greater than 1, the modulus defines the exact point where numbers stop going in a straight line and instead wrap around back to 0.
Okay.
It takes the infinite highway and bends it into a repeating cyclical structure.
And just to lay the stakes out early for you listening, without this mathematical wrapping, this cyclical racetrack, the digital security protecting your bank account wouldn't work.
At all.
Right. The data storage making your internet searches instant would completely collapse under its own weight. Even the music you listen to wouldn't sound harmonious. We are talking about the foundational rules of the modern world.
It's the bedrock.
But to understand how it powers all those massive systems, we have to understand the rules of the track, because things behave very differently here. I noticed this formal notation in the research that looked a little intimidating.
Oh, the 3 lines.
Yeah. It's written as then an equal sign with 3 lines instead of 2, then B, and then in parentheses, mod M. What does that 3-line symbol actually mean?
So that 3-line symbol denotes congruence. It is the core relationship in modular arithmetic. We say that 2 integers, a and b, are congruent modulo m.
Okay.
Formally, that means if you subtract b from a, the resulting difference is an exact integer multiple of your modulus m.
Okay, wait, you're going to have to translate that into real-world numbers for me.
Sure.
If our modulus, our racetrack size, is 10, are you saying that the numbers 12 and 22 are basically the same number in the system?
Functionally, yes.
Yeah.
Because if you subtract 12 from 22, the difference is exactly 10, which is exactly 1 multiple of our modulus, 10.
Oh, I see.
But there is a much more intuitive way to think about congruence that doesn't involve subtraction at all. It's all about remainders.
Remainders, like from long division.
Exactly. 2 numbers are congruent modulo m M, when you divide both of them by m, they leave the exact same non-negative remainder.
Ah, okay, that clicks. So if I take 12 and divide it by 10, the remainder is 2. If I take 22 and divide it by 10, the remainder is also 2. So on a modulo 10 racetrack, whether you've driven 12 miles or 22 miles, you are parked in the exact same spot. Spot number 2.
You are in the exact same spot. And this equivalence is incredibly powerful.
Why is it so powerful?
Because it allows mathematicians to take the infinite set of all integers in the universe and neatly compress them into exact disjoint subsets.
That's like sets.
Yeah, we call these subsets residue classes. If your modulus is 10, there are exactly 10 residue classes, numbered 0 through 9. Every single number that has ever existed, positive or negative, belongs to one and only one of those 10 classes.
Wow. It's like taking the infinite chaos of the universe and sorting it into 10 neat little buckets. I find that strangely comforting.
It is very tidy.
But as I read deeper, things started getting more complex. The research introduces this distinction between a complete residue system and a reduced residue system.
Right, the CRS and RRS.
Yeah, let's break those down. What is a complete residue system?
A complete residue system, or CRS, modulo M, is just a mathematical set containing exactly one representative from every single residue class.
Okay.
For modulo 10, the standard, simplest CRS is just the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. It's the complete list of all possible remainders.
Makes sense. It's just a list of all the parking spots on the track. So what makes the reduced version so special?
A reduced residue system, or RRS, is a smaller subset of that complete system. You generate it by stripping away certain numbers.
Which ones do we strip away?
Specifically, it only contains the elements from the complete system that are coprime to the modulus.
Okay, let's pause there because coprime is one of those terms that sounds self-explanatory but can really trip people up.
Fair enough.
If a number is coprime to our modulus of 10, that means they share absolutely no common factors or common divisors other than the number 1, right?
Exactly. They share no divisors.
Yeah.
And calculating exactly how many numbers survive this filtering process to form the reduced residue system is incredibly important.
How important? So important that there is a dedicated mathematical function for it. It's called Euler's totient function, which is often represented by the Greek letter phi.
Let's walk through an example of Euler's totient function because doing it manually really helped me grasp it.
Go for it.
If our modulus m is 10, our complete system is the numbers 0 through 9. To find the reduced residue system, we look at every single number and ask, does this share a divisor with 10?
Right.
If it does, we throw it out. So we eliminate all the even numbers, 2, 4, 6, and 8, because they all share the divisor 2 with the number 10.
Perfect.
We eliminate 5, because it shares 5, and we eliminate 0. After tossing all those out, we are left with exactly 4 numbers. 1, 3, 7, and 9.
Which means we can officially state that Euler's totient function of 10, or of 10, equals 4.
Because there are 4 numbers left.
Right. The size of the reduced residue system is exactly 4. Now, this might just seem like a fun parlor trick right now, but I promise you, understanding the size of this specific subset is going to become absolutely critical later. Critical for what?
For when we talk about how modern encryption algorithms lock and unlock data.
Oh, man. Okay, I'll keep that in my back pocket. Now, my absolute favorite part about learning the rules of this racetrack is how it casually bends the traditional rules of arithmetic we've all relied on since childhood.
It does get a little weird here.
Yeah, you can add numbers together, you can subtract, you can multiply perfectly fine, but then the research casually drops this bomb. Division doesn't really exist here.
It is a jarring realization.
Oh.
Traditional fractional division completely breaks down in modular arithmetic.
Why?
Well, you cannot just divide a by b and expect a functional answer because fractions like 1/2 or 3/4 don't exist in a system composed entirely of integer remainders.
Right, there's no half a parking spot.
Exactly. Instead, if you want to perform the functional equivalent of division, you have to multiply by something called a modular multiplicative inverse.
A modular multiplicative inverse, I have to say, that sounds like a defensive spell from a high fantasy novel.
Yeah. It does have a magical ring to it. But conceptually, it's quite grounded. The inverse of a number a is simply another number x that, when you multiply them together on the racetrack, lands you exactly at the number 1.
Okay.
So the equation is that times x is congruent to 1 modulo m.
But hold on, the research makes a very stern point here. It says this magical inverse doesn't always exist. You can't always find an x.
That's the catch. The inverse of a only exists if a and the modulus m are coprime.
Ah, co-prime again.
Right. If they share any factor other than 1, finding that inverse is mathematically possible. You will spin around the racetrack forever and never land exactly on the number 1.
That's wild.
But if they are coprime, you can calculate the inverse using a brilliant piece of historical mathematics called the extended Euclidean algorithm.
Okay, you need to slow down and explain the extended Euclidean algorithm because that part of the research was incredibly dense for me. How does it actually find the inverse?
To understand it, we first have to understand Bézier's identity.
Bézier's identity.
Yes, which states that for any two integers, a and b, you can always find two other integers, x and y, such that a times x plus b times y equals their greatest common divisor.
Okay, I'm following.
The extended Euclidean algorithm is essentially a way of working backward through the steps of standard division to discover those exact coefficients. When your numbers are coprime, their greatest common divisor is 1.
Right.
So the algorithm works backward until it isolates the exact multiplier x that gets you to 1, modulo m. It is a methodical, step-by-step unspooling of the relationship between the two numbers.
Okay, so that is how we hack our way around division. We find a multiplier that mimics it.
Exactly.
But what about exponentiation? What happens when we need to raise a number to a massive power? The research notes that trying to do this the traditional way would be a computational nightmare.
Oh, it would be a disaster.
It says calculating huge powers would instantly crash a modern computer via integer overflow.
Yeah, think about the physical mechanics of a computer's memory. A processor allocates a specific number of bits to store a number.
Like memory slots.
Right. If you ask a computer to take a massive number, say 500 digits long, and raise it to the power of another massive 500-digit number, the intermediate mathematical result would be astronomically large.
The intermediate result.
Yeah, the number generated before you even get a chance to apply the modulus and shrink it down, it would require more memory bits than the computer physically has.
Oh, wow.
The number overflows the allocated memory buffer and the system literally crashes. It panics.
So how do we stop the computer from panicking? If we need to calculate these massive exponents for cryptography, how do we keep the intermediate numbers small?
The solution is an incredibly elegant algorithmic shortcut called binary exponentiation,
Okay.
which is also known as the square and multiply method. Instead of calculating the massive exponent all at once in one giant leap, the computer breaks the exponent down into its binary representation.
Like a long string of ones and zeros.
Exactly. Then it calculates the power step by step. And here's the genius part. It applies the modulus after every single square or multiplication operation.
Ah, so you never give the number a chance to get too big. You multiply, it gets a little bigger, and instantly you pull it back down to the racetrack.
You got it. You chop the mathematical workload down to what computer scientists call an O of log E, time complexity. By reducing the number at every microstep, you ensure that the intermediate numbers never ever exceed the square of the modulus.
That is just brilliant engineering.
It really is.
Yeah.
The computer's memory buffer is perfectly safe, and a calculation that would have taken a classical supercomputer until the end of the universe to solve is executed in literal milliseconds.
Keeping the race car tightly on the track instead of letting it fly off into deep space and explode. I love it.
Yeah.
Now, to close out the foundational section of our research, we have to talk about the heavy hitters, the theoretical backbone of everything we're going to discuss today, the big three theorems.
Oh, yeah. Fermat's little theorem, Euler's theorem, and the Chinese remainder theorem.
Yes. These three theorems are they're the absolute pillars of all modular applications. Let's start with Fermat.
Right, so Fermat's little theorem is a beautiful proof which states that if you have a prime modulus, let's call it p, and you take any number and raise it to the power of p minus 1,
Okay.
it will always loop you perfectly around the track to land exactly on the number 1.
Always.
Always. And then Euler's theorem is the evolutionary next step. It generalizes Fermat's rule so it works for any modulus, not just prime numbers.
How does it do that?
By utilizing that totient function we calculated earlier, the phi function.
Look at that coming back already.
Okay.
And then there's the Chinese remainder theorem, or CRT. I spent a lot of time on this one.
It's a fun one.
And the way I visualize the CRT is like delegating a massive, impossible project.
Okay, tell me more.
So imagine you have a gargantuan computational problem with a modulus so large it's unwieldy. It is simply too big for one person or one processor to solve efficiently.
Right.
The CRT proves that you can split that one gigantic problem into parallel independent tasks over smaller moduli. You solve those smaller chunks simultaneously, and then you perfectly combine the results into the one unique correct answer.
That is a highly accurate analogy, and it really reflects the theorem's historical origin.
Historical origin.
Yeah. The Chinese remainder theorem dates back to the 3rd century, formulated by the mathematician Sun Tzu. Not the Art of War author, a different Sun Tzu.
Oh, wait, really? A different one?
Yeah, different guy. But he posed a problem. Imagine you have an army, and you need to know exactly how many soldiers you have, but counting them one by one takes way too long.
Sure.
So you tell the soldiers to stand in rows of 3, and you count the remainder. Then rows of 5, count the remainder. Then rows of 7, count the remainder.
Okay.
The CRT proves that if the moduli are pairwise coprime, meaning 3, 5, and 7 share no common factors with each other, those 3 small remainders give you enough information to calculate the exact unique number of total soldiers in the army.
That is staggering. It's the ultimate divide and conquer strategy in mathematics.
It really is.
Instead of struggling with a massive data set, you break it down, distribute the work across smaller, manageable tracks, and reassemble it with absolute mathematical certainty.
Exactly.
Okay, so we've established the rules of this strange universe. We know how numbers wrap around, how we avoid dividing, how we prevent computers from memory crashing, and how we delegate massive computations. But it is time to ground this in reality.
Let's do it.
How do these abstract 3rd century rules actually protect my bank account today?
Well, if we connect all these theoretical rules to the modern digital landscape, modular arithmetic provides something incredibly rare and highly prized in computer science.
What's that?
A practically perfect one-way function.
Okay, clarify what a one-way function is in this context.
Think of it as a mathematical process that is trivial to perform in one direction, but almost computationally impossible to reverse engineer.
Like smashing a vase.
That is the perfect analogy. It is very easy to smash a vase into 1,000 pieces. It is incredibly difficult and time-consuming to take those 1,000 pieces and reconstruct the exact original vase.
Right.
Right.
That asymmetry, that one-way street, is the absolute foundation of digital trust and modern cryptography.
So let's dive into the first major cryptographic application mentioned in the research, RSA encryption. If anyone listening has ever done something online using a credit card, you have used RSA.
Oh, absolutely. It is the gold standard for asymmetric cryptography.
Asymmetric being the key word there.
Yes. In the old days of cryptography, you had symmetric keys, a single password that both locked and unlocked a file.
Right, like a combination lock on a safe.
Exactly. The problem was, how do you safely give the password to the recipient without someone intercepting it?
Yeah, if the mailman steals the password, your safe is useless.
Right. So asymmetric cryptography solves this by using 2 different mathematically linked keys. A public key that you give to the world to lock messages meant for you, and a private key that you keep entirely secret to unlock them.
And the research states that the security of RSA is built entirely on the computational nightmare of factoring the product of 2 massive prime numbers.
Yes, it is. Let's walk through this pipeline step by step, because the architecture here is just a masterpiece. I want to understand exactly what my computer is doing in the background. First, the key generation.
Right. It starts with your computer randomly selecting 2 very large, completely distinct secret prime numbers.
Okay.
Let's call them P and Q. In real-world applications today, these primes are often hundreds of digits long. The computer multiplies them together to get your public modulus, N.
So N is public.
Yes, this N defines the size of your cryptographic racetrack. And because it's public, you broadcast it to the whole world.
Wait, if I'm broadcasting N, aren't I giving hackers the answer? Why doesn't a hacker just look at N and figure out what P and Q are?
Because of the one-way function. Multiplying P and Q together is mathematically trivial. It takes a fraction of a millisecond.
Okay.
But taking that massive 600-digit number N and working backward to figure out the 2 original prime factors is computationally devastating.
So the vase is smashed.
Exactly. There is no known fast algorithm for integer factorization. It would take a classical supercomputer, thousands, perhaps millions of years of brute force guessing to find them.
Okay, so the foundation is secure. We have our public N. What's next?
Next, the system uses those secret primes to calculate Euler's totient function for the system.
The phi function again.
Right. Once it has that, it selects a public encryption exponent, E. The research notes that E is very commonly chosen to be the number 65,537.
That seems incredibly specific. Why 65,537?
It's chosen for pure computational efficiency. 65,537 is a prime number that has a very specific binary representation. is mostly zeros with just 2 ones.
Oh.
Yeah, that makes the binary square and multiply algorithm we discussed earlier run incredibly fast for the person encrypting the message without sacrificing any security.
That's so clever.
Once you have your public E, your computer calculates your private decryption key, D,
How does it get D?
by using the modular multiplicative inverse,
Mm.
specifically the inverse of E modulo, the totient function.
I feel like I'm holding all the pieces of a puzzle. So the public has N and E. That's the open padlock. Anyone can use it.
Yep.
But only I have D. That's the physical key to unlock it.
Correct. The encryption pipeline is simple. The sender takes their plain text message, M, converts it into an integer, and raises it to the power of the public exponent E modulo N.
And that scrambles it.
That chaotic math scrambles the data and creates an unrecognizable ciphertext, C.
And here is the absolute aha moment for me. When I was reading the decryption pipeline, I literally gasped.
It's pretty amazing.
Because to decrypt that scrambled ciphertext C, the recipient just takes it and raises it to the power of their private key D modulo N. And somehow the scrambled math loops perfectly around this massive racetrack and lands exactly, unambiguously, back on the original plaintext message M.
It is breathtaking the first time you see the proof. And it's not magic, it is Euler's theorem from our foundation section. Because of how the private key D was generated, using the multiplicative inverse relative to the totient function, the exponent math perfectly cancels itself out.
It cancels out.
C to the power of D is congruent to the original message M, multiplied by an astronomical loop of ones. The message travels around the racetrack an unimaginable number of times, spinning wildly and mathematically must slam on the brakes on the exact same residue class it started on.
It's a perfect mathematical boomerang. You throw it into the chaos and it returns perfectly intact. But RSA isn't the only way to secure a digital connection.
Yeah, it's not.
The research also details something called the Diffie-Hellman key exchange, and I had a major conceptual block when I first read about this.
Oh yeah, what was the block?
Here is my question. If Alice and Bob have never met, how do they agree on a secret shared password over an open internet connection where literally everyone, including hackers, is listening to every word they say?
It seems like a complete paradox, doesn't it?
Yeah.
How do you share a secret in a crowded room by shouting across the room?
Right.
Diffie-Hellman solves this paradox using a completely different one-way function called the discrete logarithm problem, or DLP.
The discrete logarithm problem. Explain why this is hard to solve.
Well, while it's computationally trivial to take a number, raise it to a power, and find the remainder modulo M, it is practically impossible to do the reverse.
So if you give me the answer, I can't find the exponent.
Exactly. If I give you the final remainder, the base number, and the modulus, there is no efficient algorithm to figure out what the original exponent was. The math is too chaotic. The wrapping around the track obscures the history of the number.
Okay, so how do Alice and Bob use this to their advantage?
Here is the algebraic magic. Alice and Bob publicly agree on a massive prime modulus P and a base number called a generator G. They shout these across the room. Everyone can hear them.
Okay, P and G are public.
Now, Alice secretly chooses a random number, A. She calculates G to the power of A, modulo P. She sends that scrambled result to Bob.
And Bob does the exact same thing on his end. He secretly picks a random number B, calculates G to the power of B, modulo P, and sends his scrambled result to Alice. So the hackers listening in the room only see the publicly agreed numbers and the two scrambled results. They have no idea what the secret exponents A or B are.
Right, and because of the discrete logarithm problem, the hackers can't figure them out.
Okay, so what's the secret convergence?
Alice takes Bob's scrambled number, and she raises it to her secret power, A. Bob takes Alice's scrambled number, and he raises it to his secret power, B.
Oh.
Because of the associative property of exponents in modular arithmetic, G to the power of B, then raised to A, is mathematically identical to G to the power of A, then raised to B.
So they independently arrive at the exact same massive shared number without ever actually transmitting the number itself.
Yes.
I was trying to picture this, and the best analogy I could come up with is mixing paint.
I love this analogy.
It's like Alice and Bob both start with a public bucket of yellow paint. Alice secretly adds red paint, mixes it up to make orange, and throws it across the room to Bob. Bob secretly adds blue paint to his yellow, mixes it to make green, and throws it to Alice.
That's a classic cryptographic visualization.
Right. So the hacker only catches the orange paint and the green paint, but it is physically impossible to unmix paint.
Right. You can't pull the red out of the orange.
Exactly. The hacker can't extract Alice's secret red or Bob's secret blue, But Alice just takes Bob's green paint, adds her secret red, and Bob takes Alice's orange paint, adds his secret blue. They both end up with the exact same muddy brown color.
And that muddy brown color is their shared encryption key.
That is so cool. The paint analogy beautifully illustrates the one-way nature of the exchange. And once they have that shared key, they use it to securely encrypt the rest of their conversation.
Right. Now, both RSA and Diffie-Hellman have been the backbone of the internet for decades, but the research highlights a modern upgrade that is vital to discuss.
Oh yes, here's where it gets really interesting. Elliptic curve cryptography, or ECC.
ECC is fascinating.
The research document points out a staggering leap in efficiency here. It states that a tiny 256-bit ECC key provides the exact same level of cryptographic security as a massive 3072-bit RSA key. I don't understand how that is physically possible. How can a tiny key be just as strong as a giant one?
It's possible because ECC completely changes the physical shape of the racetrack.
How so?
Instead of working with simple integers on a basic circular loop, ECC constructs an algebraic group over a finite field using a highly complex geometric curve.
Okay, I'm trying to picture it.
The underlying equation looks something like y squared is congruent to x cubed plus x plus b modulo a prime b.
You're losing me. We're mapping a swooping, continuous geometric line onto a discrete modular grid.
Exactly. Imagine a standard continuous curve on a graph, but then you apply the modulo p to the coordinates. The continuous line shatters into a scattering of distinct mirrored points on a grid.
Shattered points.
Oh.
Okay.
And instead of multiplying massive numbers together like RSA, the fundamental mathematical operation in ECC is point addition on this shattered curve.
Okay, what does point addition actually look like?
Geometrically, you take a starting point on the curve, let's call it P. You find another point Q. You draw a straight second line through them. You follow that line until it intersects the curve at a third point.
Okay.
Then you reflect that point straight down across the x-axis to find your final point, R. Doing this repeatedly, drawing lines, intersecting, reflecting, is the ECC equivalent of multiplying numbers.
That sounds wildly complicated for a computer processor to calculate for every single encryption step. Drawing geometry.
Geometrically, yes, it sounds complex. But algebraically, the computer isn't drawing anything. It calculates the coordinates of that final point R using algebraic slope equations.
Ah, right. It's just math.
And here is where the entire system connects back to our very first topic. To calculate the slope of that intersecting line, the computer has to perform fractional division.
Right.
And as you noted in section 1,
Fractional division doesn't exist on the racetrack. You have to use the modular multiplicative inverse.
exactly, the exact same foundational rule we established at the beginning, using the extended Euclidean algorithm to find the inverse, is executing the slope calculations for the most advanced cryptographic curves in the world.
That is wild.
Reversing this geometric point addition process is called the elliptic curve discrete logarithm problem. It is so mathematically dense, so incredibly chaotic, that you can achieve unbreakable security with a tiny fraction of the key size.
So it's way faster.
Much faster. This optimizes processing power, saves massive amounts of battery life on mobile devices, and reduces bandwidth for things like secure web browsing, iMessage, and modern cryptocurrency ledgers.
It's just a tighter, far more brutal one-way street. That is amazing.
Yeah, it is.
Okay, so we spent a lot of time on how we use this math to hide and protect data from bad actors. But as we transition into the next phase of our research, we move from hiding data to simply storing and processing it.
Right, the everyday operations.
Yeah. Even when we aren't trying to protect nuclear launch codes or bank transfers, we are using modular math just to keep our digital world from collapsing. Let's talk about computer science and data architecture.
This is a fascinating pivot, because in computer architecture, modular arithmetic acts less like a padlock and more like a high-speed traffic controller.
A traffic controller? Like what?
A prime example of this is hashing functions and hash tables.
Right. From what I understand, a hash table is basically a way for a database to map an arbitrary key, like a user's randomly generated screen name or an alphanumeric file ID, to a fixed size array so the computer can retrieve it instantly.
They call it O of 1 data retrieval.
And the core mechanism powering this instant search is the modulo division method.
Yes. The formula is elegantly simple. The hash of the key equals the key modulo m, where m is the total number of storage slots in your array.
I picture this like trying to sort millions of random, unorganized files into a room that only has 100 fixed filing cabinets.
Okay, good visual.
You can't just put them in randomly, or you'd have to search every single cabinet to find a file again, which takes way too long.
Right.
Instead, you take the file's ID number, divide it by 100, and whatever the remainder is, say 42, you confidently put the file in cabinet number 42. When you need that file a year later, the computer does the math instantly, walks right to cabinet 42, and pulls it out. No searching required.
That's a perfect visualization of how it should work.
Huh.
But the research points out a critical systemic danger in how an engineer chooses the number of filing cabinets, your modulus M.
What's the danger?
If you choose a composite number, specifically an even power of 2, like m equals 2 to the power of k, you create a massive hazard for your database.
Why is a power of 2 dangerous? I thought computers operate in binary. They love powers of 2.
They do operate in binary, but mathematically, taking a number modulo 2 to the power of k using bitwise operations simply strips away all the higher bits of the key's binary representation.
It just chops them off.
Basically, yeah. It ignores the bulk of the data and only looks at the very lowest bits. If your input data happens to share common factors or follows any sort of repetitive arithmetic pattern, which user data almost always does, those lower bits will be identical.
So what happens physically in the server farm?
All your files will map to the exact same filing cabinet. It causes massive data collisions.
Oh, no.
Yeah. Cabinet 42 is overflowing with thousands of files, while cabinets 1 through 41 are completely empty.
So the shortcut is ruined.
Completely. When you go to retrieve a file from cabinet 42, the computer has to sort through thousands of files manually, destroying your retrieval speed.
That's a huge problem.
This isn't just an inconvenience, it's an attack vector. Hackers use this specific vulnerability to launch algorithmic denial of service attacks, intentionally feeding a server inputs that all hash to the same slot until the server's CPU hits 100% and crashes.
So how do you fix it? How do you prevent the data pileup?
System architects champion something called the prime modulus advantage.
Primes?
Primes again. By choosing a large prime number for your modulus M, you ensure that every single bit of the original key high bits and low bits contributes to the final index calculation.
How does that help?
Because a prime number doesn't share factors with the natural patterns of the data, it acts as an algorithmic blender. It guarantees uniform data distribution across all your cabinets, keeping the system lightning fast and resilient to attacks.
Prime numbers really are the VIPs of computer science. It's like they hold the whole structure together.
They absolutely are. What's fascinating is that while prime numbers are used to perfectly organize data, computer scientists use composite numbers to generate digital chaos.
Yes. Creating randomness. I have always wondered about this. A computer is purely logical. It follows exact deterministic instructions. It has no imagination. So how on earth does a rigidly logical machine create a random number for a video game or a statistical simulation?
The profound truth is, it doesn't.
It doesn't.
No. A traditional computer cannot generate true randomness. It creates a pseudorandom number.
Pseudo-random.
And one of the oldest and most fundamental algorithms to achieve this illusion of randomness is the linear congruential generator. It uses a linear recurrence relation modulo M.
Let me make sure I have the formula right. The next number in the sequence equals a multiplier times the current number plus an increment c, all modulo M.
Correct. It takes a starting seed number, maybe the current millisecond on the computer's internal clock, multiplies it, adds a constant to it, and drops it onto the racetrack.
Okay.
Wherever it lands is your random number. Then, crucially, it takes that landing spot and uses it as the new seed for the next round.
But if it's just following a formula, couldn't it get stuck? Like if you just pick random numbers for A, C, and M, couldn't the generator get trapped in a tiny loop repeating the same 3 numbers over and over? That would be a terrible random number generator.
Exactly. To create a sequence that appears truly chaotic and random, the sequence must hit every single residue position on the racetrack exactly once before it ever repeats. It must have a full period.
It has to visit every single parking spot on the track before it goes back to the beginning.
Yes. And the exact mathematical conditions required to achieve this full period sequence are rigorously defined by something called the Hall-Dobell theorem.
I loved reading this part of the research because the rules are so intensely strict. First, the increment c and the modulus m must be coprime.
Right.
Second, if you take the multiplier and subtract 1, so a minus 1, that result must be divisible by every single prime factor of m.
Correct.
And third, if m happens to be a multiple of 4, then a minus 1 must also be a multiple of 4.
It is a very rigid mathematical lock. If you fail even one of those conditions, your randomness collapses. If you meet all 3, your generator achieves maximum statistical distribution.
It's amazing that we figured that out.
The research actually shares the specific legacy specifications for the GLIBC compiler, a foundational piece of software infrastructure, as a concrete example of the whole Dobell rules in action.
Let me read these numbers because they sound absolutely insane when you say them out loud.
Go ahead.
To get perfect pseudorandomness, the software developers set the modulus m to 2 to the power of 31. They set the multiplier a to exactly 11,103,515,245. And they set the increment c to 12,345.
Quite a list.
Those specific chaotic-sounding numbers weren't pulled out of thin air. They were carefully chosen because they perfectly, flawlessly satisfy the whole Dobell theorem.
It is precision engineering applied to pure mathematics. And this structural use of modulo math extends far beyond just hashing and random numbers. It permeates data architecture. The research rapidly connects the dots across several distinct tech fields, for instance, circular buffers.
Right. Using modular increments to seamlessly loop pointer positions in a fixed-size memory queue.
Exactly.
So when a continuous stream of data comes in, like live audio processing, the system just overwrites the oldest data naturally, wrapping around the track so you never have to waste processing power physically shifting data chunks around in memory.
It's also vital in 2D to 1D mapping. Hardware memory arrays on a microchip are physically flat and linear.
Right. There's no actual 3D space in the chip.
Yeah. So to store a multi-dimensional matrix, like an ultra-high-definition image with rows and columns of pixels, the computer uses modular division to map those 2D geometric coordinates into a single 1D index array and then translates it back instantly when rendering the image to your screen.
The research also dives into distributed database resharding.
That's a big one for cloud computing.
When a massive tech company needs to upgrade its server farms, scaling up from 10 massive databases to 15 without taking the system offline, they solve massive systems of linear congruences to map out exactly how the data needs to migrate.
Right, it dynamically balances the load.
Yeah, minimizing network traffic so the entire infrastructure doesn't crash during the transition.
But perhaps the most cutting-edge, fascinating application mentioned in this section is in the realm of modern artificial intelligence and machine learning.
Yes, cyclical feature engineering. I wanted to spotlight this because it is such a clever human solution to a machine problem.
It really is.
The research explains that an AI model, by default, is kind of dumb when it comes to human cycles. If you feed an AI raw chronological time data to predict, say, electricity usage, the AI looks at the data and thinks 23.0, or 11 p.m., and 00.00, midnight, are 23 hours apart.
It just sees the integers 23 and 0.
Exactly. And structurally assumes they are at opposite distant ends of the numerical spectrum.
Which fundamentally breaks any predictive model trying to understand late-night human behavior. Because in reality, 11 p.m. and midnight are obviously right next to each other. The transition is seamless.
So how do data engineers teach a rigid AI that time actually wraps around?
They use modulo 24.
They project the timeline onto a 2D circle using sine and cosine transformations. By mapping the hour of the day onto a unit circle using trigonometric functions based on modulo 24, they literally bend the AI's mathematical perception of the timeline.
It's a brilliant structural manipulation. The AI no longer sees a straight finite line from 0 to 23. It sees a geometric circle where the coordinate for 23 is physically, mathematically, directly adjacent to the coordinate for 0.
You are using cyclical math to teach a machine how to accurately perceive the human experience of time.
It's incredible. We literally have to translate our reality into modular equations so machines can understand us.
And speaking of the human experience, I think it's time we shift our focus. We've seen how machines perfectly execute this math in the background, but what happens when you introduce clumsy human fingers into the mix?
The inevitable human error.
Right. When a tired cashier types a product code wrong, or you miskey your credit card number, how does the math catch our mistakes?
This is a crucial application. Whenever you transmit data, whether it's over a noisy radio channel with static or just a human rushing through a checkout line, mistakes inevitably happen.
Digits get changed, skipped, or swapped.
Exactly. To catch these mistakes instantly, without forcing the system to query the main database and re-verify the entire string of numbers every single time, engineers embed mathematical check digits into the codes using modular equations.
Let's start with a classic, the UPC barcode. The standard 12-digit system printed on almost every consumer product you buy at the grocery store.
We scan them every day.
The research breaks this down beautifully. The first 11 digits are the actual information. the manufacturer ID and the specific product ID, but that 12th digit at the very end is the automated validation check digit.
And the way the scanner validates the barcode is by applying an alternating weight pattern modulo 10.
How does that work?
When the laser scans the code, the computer takes the first digit and multiplies it by 3. It takes the second digit and multiplies it by 1, third digit by 3, fourth by 1, and so on.
Okay, alternating 3s and 1s.
Right, it adds all those weighted numbers up, including the final check digit. For the scan to be accepted as valid, the grand total sum must be exactly congruent to 0 modulo 10.
In other words, after all that multiplication and addition, the grand total has to end in a 0.
Correct. And the research provides a rigorous mathematical proof of why this specific alternating pattern of 3s and 1s is so highly effective. It guarantees that the system will catch 100% of single-digit typos.
Okay, let's unpack that proof. If I'm the cashier and I manually type a 7 instead of a 4, why is the system guaranteed to catch my mistake?
Because of how the weights interact with the error. The typo changes the total checksum by a very specific delta, the difference between the wrong number and the right number, multiplied by whatever the weight was for that position, either 3 or 1.
Okay, so 7 minus 4 is a difference of 3.
Right. Multiply that difference by the weight. Let's say it was in a position weighted by 3, and your total sum is now off by exactly 9. For an error to slip past the system undetected, the new incorrect sum would still have to be a multiple of 10.
Meaning the delta itself, the change you introduced, would have to be divisible by 10.
You got it.
And because you are only swapping a single digit, the maximum possible difference between any two single digits is 9. And no number between 1 and 9 is ever divisible by 10. Therefore, the sum will never end in a 0, the modulo math fails, and the cash register will instantly beep and say, invalid code.
Exactly. The mathematics physically guarantee that a single-digit fault cannot naturally recreate a valid modulo 10 checksum.
Okay, I have to push back a little here. Is the system really foolproof? What if I make a different kind of mistake? What if I'm typing really fast?
It is definitely not foolproof. The expert analysis in the research reveals a very specific structural vulnerability in the UPC system, adjacent transpositions.
Oh, like when you accidentally swap two numbers side by side, you type 4-7 instead of 7-4.
It's arguably the most common human typo.
I do that all the time.
When you swap two adjacent digits, the math changes. Originally, one of those numbers was being multiplied by 3 and the other by 1. By swapping their positions, they switch weights.
Okay, I see where this is going.
If you run the algebra on this transposition, the change to the total sum simplifies elegantly. The delta is exactly 2 times the difference between the two swapped numbers.
Okay, 2 times the difference. And for the error to go undetected by the register, that delta still has to be a multiple of 10.
Right. So the equation is 2 times the difference is congruent to 0 modulo 10, which means the difference between the two swap numbers must be exactly 5.
Wait, oh, because 2 times 5 is 10.
Exactly.
So if the two adjacent numbers on the barcode happen to have a difference of exactly 5, like 2 and 7 or 4 and 9, and you swap them, the system gets completely tricked. The math perfectly balances out, the new sum still ends in a 0, and the scanner happily accepts an entirely incorrect product code.
It is a massive blind spot, and it is entirely created by the choice of a composite modulus, the number 10. Because 10 shares factors with the weights, it allows these localized errors to mathematically cancel each other out.
And this brings us to the publishing industry, which I was fascinated to learn actually solved this exact transposition vulnerability using the older ISBN 10 standard for cataloging books.
Yes, the ISBN 10 algorithm is a masterclass in applying abstract mathematical theory to solve a tangible real-world problem.
How does it fix it?
Instead of repeating 3 and 1 weight pattern modulo 10, ISBN 10 uses a linearly decreasing weight pattern multiplying the first digit by 10, the second by 9, then 8, all the way down to 1. But the crucial architectural change is that the entire system is evaluated modulo 11.
Modulo 11, the prime modulus advantage strikes again. Primes fixing the flaws of composites.
Exactly, because 11 is a prime number. Every single weight multiplier from 1 to 10 is perfectly co-primed to it.
Right.
This structural change provides an enormous mathematical advantage. Like the UPC, it catches 100% of single-digit errors. But unlike the UPC, the prime modulus eliminates the transposition vulnerability entirely.
Let's explain why. If you swap two adjacent numbers in ISBN 10, the difference in the final sum has to be a multiple of 11 to go undetected.
Right.
But the maximum difference between any two single digits on a keyboard is 9. You can never, ever reach 11.
Ever.
Therefore, it is mathematically impossible for an adjacent transposition to slip past an ISBN 10 check. It catches 100% of them.
It is mathematically airtight. And this elegant system also explains a very quirky historical artifact in publishing.
Oh, I love this part.
Because the system is modulo 11, the required check digit generated at the very end of the equation might occasionally need to be the number 10 to make the math perfectly balance out to 0.
Right, but you can't put a two-digit number 1 and 0 in a single character slot on a barcode. It ruins the length.
So what do?
They use the Roman numeral for 10, the mysterious X that you see on the back of older books. I spent my whole childhood wondering why some books had an X instead of a number. It's literally just the number 10 acting as a placeholder in a modulo 11 math equation.
It's a beautiful, tangible intersection of history and pure math. However, as the research tragically points out, modern books now use the ISBN 13 standard.
Yes, which reverted entirely back to the UPC modulo 10 system with the 3-in-1 alternating weights.
They took a step backward.
They did it just to match global retail barcode scanners. They knowingly sacrificed perfect mathematical security for commercial logistical convenience and intentionally reintroduced the exact same transposition vulnerabilities into the global book industry. It honestly breaks my heart a little bit.
It's a classic engineering trade-off. Standardization and global compatibility often win out over mathematical perfection. But this brings us to the highest stakes error detection system mentioned in the research, the Loon algorithm.
Credit cards. When I am typing my 16-digit Visa or MasterCard number into a website to buy something, this is the algorithm checking my work before it even hits the bank's servers.
Yes, the Loon algorithm, created by Hans-Peter Loon at IBM in the 1950s, is the global Mod 10 validation standard.
How does it work?
It's slightly more complex than a standard barcode check. Moving right to left across your credit card number, the algorithm doubles every second digit.
Okay.
But if that doubling operation results in a number greater than 9, for example, if the digit is 7, 7 times 2 is 14, you don't use 14. You add the digits of that result together. 1 plus 4 is 5.
And the research notes a really cool computational trick for this. Adding the digits of a doubled number together is mathematically identical to just subtracting 9 from the product. 14 minus 9 is 5. It's a much faster operation for a computer.
Exactly. It's a process called a digital root reduction. Once the algorithm reduces all the doubled numbers, it adds everything together, the undoubled digits and the reduced digits, and the grand total sum must be congruent to 0 modulo 10.
Modulo 10 again.
The research provides a deep analytical look at how this specific function maps the digits. By doubling and reducing, it maps every input digit 0 through 9 to a completely unique output digit.
Because it's a perfect permutation mapping, it instantly catches any single-digit error, just like the UPC code.
But its real strength, and the reason it was chosen for global finance, is in handling transpositions. When you evaluate the change caused by swapping two adjacent digits using this specific doubling and reduction function, the algorithm successfully catches almost every single transposition error.
Almost.
With one highly specific mathematical exception.
Swapping a 0 and a 9.
Yes. Let's look at the math. If you evaluate the Loon function for the digit 0, doubling it yields 0.
Right.
If you evaluate the function for the digit 9, doubling it is 18, and 1 plus 8 is 9. It yields 9.
Okay.
Therefore, the change in the delta when you accidentally swap a 0 and a 9 perfectly cancels itself out, modulo 10. It is the single blind spot in the Loon algorithm. If your credit card happens to have a 0 and a 9 right next to each other, and you type 90 instead of 09, the browser validation will mathematically accept it as a valid card.
So what happens then? Does the charge go through?
No, the charge will ultimately bounce. But it bounces at the bank's back-end server level instead of instantly at your browser level, which consumes network resources and delays the transaction.
That is wildly specific, but so satisfying to finally know the exact mathematical limitation of the system validating the world's money.
It's good to know the limits.
All right, as we move into the final phase of our deep dive, I want to pull us away from the digital networks, the cryptography, and the commercial realms. Let's step into the deeply human spheres, how we intuitively structure our lives, and how we create art. This is where the math of time and sound comes into play.
It's a very fitting transition, because time and music are fundamentally, inextricably cyclical experiences. They're the original racetracks.
Let's talk about time and calendars first. The research points out something so obvious I had never considered it. We all natively, intuitively think in modular arithmetic when it comes to time. We use modulo 12 or modulo 24 for clocks and modulo 7 for the days of the week.
We do it constantly without even realizing we are performing advanced modular reductions. The research gives a perfect example. If an IT worker sets a server to run a 15-hour automated process starting at 1300 or 1 p.m., they don't say the process finishes at 28.0.
No, that would sound ridiculous.
The human brain intuitively calculates 28 modulo 24, drops the excess, and arrives at SU 4.0 or 4 a.m.
We've been doing modulo equations since we learned how to read a clock in the first grade, but my absolute favorite part of the calendar section, the part I fully geeked out over, was Zeller's congruence.
Oh, Zeller's congruence is amazing.
It is an algorithm that can mathematically calculate the exact day of the week for any date in recorded Gregorian history. You give it a random date in 1742 and it spits out Tuesday. And it does it by mashing several different time cycles into a single unified equation modulo 7.
Zeller's congruence is a fascinating piece of recreational mathematics that actually sees heavy use in back-end programming. It accounts for the day of the month itself, the specific year of the century, and the zero-based century. All of these variables flow into a single modulo 7 reduction to output a neat little integer from 0 to 6, representing Saturday through Friday.
But I kept thinking, how does an algorithm handle leap years? Because the fact that February has an extra day every 4 years completely ruins the clean, cyclical math of the calendar. It throws everything off.
This is a messy human complication.
So how does Zeller's algorithm fix it? It does something totally unhinged but completely brilliant. It structurally treats January and February not as the first 2 months of the year, but as month 13 and month 14 of the previous year.
It is a deeply elegant mathematical hack to solve a messy human problem. By shifting January and February to the end of the calendar mathematically, the leap day, February 29th, is pushed to the absolute very end of the mathematical cycle.
Right.
It prevents that extra day from disrupting all the intermediate calculations of the algorithm. It's computational self-defense against the chaos of the Julian calendar.
Literally changing the foundational definition of a year just to keep the modulo math clean. I love the audacity of it. Okay, let's transition from the macro cycles of time to the microcycles of frequency, music theory, and acoustic aesthetics.
While music is generally experienced by humans as a purely emotional, intuitive medium, its underlying structure is rigorously, inflexibly mathematical. And it all begins with the physical concept of octave equivalence.
Right. The research defines this physically.
Yeah.
If you have a sound wave vibrating at a certain frequency, say 440 hertz, and you perfectly double that frequency to 880 hertz, the human ear perceives a note that sounds fundamentally identical.
Exactly.
It is the same note, just higher pitched.
That physical psychoacoustic phenomenon defines an equivalence relation over physical frequencies. It takes an infinite continuous spectrum of audible sound and groups it into distinct repeating pitch classes. In Western music, specifically the framework known as 12-tone equal temperament, or 12TE, we chop the acoustic space between an octave into 12 perfectly equally spaced semitones.
And by assigning numbers to those 12 semitones, 0 for C, 1 for C sharp, 2 for D, all the way up to 11 for B, the musical octave forms a perfect cyclic mathematical group, Z12.
Exactly. The musical octave is mathematically identical to a clock face.
Yeah.
And because it's a closed modulo 12 system, structural musical alterations that composers make can be expressed as precise geometric transformations.
The research maps this out perfectly. Transposition, which is when you shift a melody up or down into a new key so a singer can comfortably hit the notes, is literally just modular addition.
Yeah.
You take the melody's numerical notes, add n semitones to each one, and apply modulo 12.
On inversion, flipping a melody upside down around a reference note to create a mirror image is simply modular subtraction or negation. The equation is the inverted note equals 12 minus the original note, modulo 12.
The research mentions that these exact mathematical operations form the dodecaphonic group, which was the structural framework for Arnold Schoenberg's 12-tone serialism in classical music. The man was basically composing music using pure modular algebra. He built prime, inverted, and retrograde matrices. It's high-level math disguised as avant-garde art.
Or perhaps art is just the human expression of underlying mathematics, which brings us to the ultimate synthesis of music and math in the research, the circle of fifths.
This was the big payoff for me. So what does this all mean for the listener? Why are some chords perfectly harmonious, moving the song forward and feeling comprehensive, while other chord progressions just feel stuck in place, eerie and unresolved?
Group theory holds the exact answer. The circle of fifths is a conceptual tool that illustrates how musical keys mathematically relate to each other. A perfect fifth interval spans exactly 7 semitones.
Okay.
If you start at the note C, which is 0, and repeatedly add 7 modulo 12, you generate a sequence, C to G to D to A, and so on.
Let me trace the math on that. 0 plus 7 is 7. 7 plus 7 is 14, which modulo 12 wraps around to 2. 2 plus 7 is 9. It just violently hops around the clock face.
Yes, but here is the critical part. Because 7 and 12 are co-prime, they share no common factors, the number 7 acts as a generator for the cyclic group.
A generator.
If you keep adding perfect fifths, you will perfectly cycle through every single one of the 12 notes in Western music exactly once before you ever repeat a note. You traverse the entire sonic landscape. It feels complete.
It is the musical equivalent of the reduced residue system from cryptography.
Exactly. But contrast that with a major third interval, which the research explores as the counterexample. A major third spans exactly 4 semitones.
And what happens mathematically when you evaluate the relationship between 4 and 12?
They share a factor.
The greatest common divisor is 4. They're not coprime.
Exactly. Because they share a factor, the number 4 cannot generate the full musical group. If you repeatedly add major thirds, 0 plus 4 is 4, plus 4 is 8, plus 4 is 12, which wraps instantly back to 0, you create a trapped, isolated mathematical subgroup. Just the notes C, E, and G sharp, looping endlessly.
An augmented triad. You are mathematically walled off from the other 9 notes of the scale. It's stunning. The emotional feeling of musical progression, the difference between a song that moves you and a song that feels stagnant, is dictated entirely by whether the semitone interval is co-prime to the modulus 12. It all comes back to prime factorization.
It truly does. It unites the acoustic with the arithmetic.
Mm-hmm.
And as we synthesize this entire journey, looking back across all these completely diverse fields, it becomes clear that everything is governed entirely by the engineering choice of the modulus.
Let's run through it, because seeing the grand unified theory of all this together is wild. When we need impenetrable digital security and trapdoor one-way functions like RSA, we use the massive chaotic product of 2 primes. When we need smaller key sizes and geometric efficiency for TLS browsing like ECC, we use a single prime number.
When we need to sort massive server data uniformly in hash tables, we rely on the prime modulus advantage to prevent collisions. But when we want to generate chaotic pseudorandom sequences for simulations, we switch to powers of 2 to maximize the sequence length according to the rigid rules of the Holder-Bell theorem.
When we need cheap, automated consumer validation for barcodes and credit cards, we use the composite base 10, accepting its structural flaws. But when the publishing industry demanded perfect transposition error elimination for ISBN 10, they stepped up to the mathematically airtight prime modulus 11.
And finally, when modeling the human experience of chronological time or composing acoustic aesthetics, we rely on the highly composite moduli of 7, 12, and 24 to organize cycles and vector symmetry. It is all the exact same cyclical mechanics applied to vastly different structural constraints.
It really is a hidden engine running the modern world. But as we wrap up this deep dive, I want to leave you, the listener, with a final provocative thought to mull over on your own.
It's a big one.
It builds on the cryptography concepts we explored in the second half of our journey. We established that all modern digital, trust your bank account, your private text messages, the secure networks powering the global economy via RSA and ECC, relies entirely on the computational difficulty of these cyclical algorithms, the sheer impossibility of reversing the discrete logarithm problem. But what happens if a new mathematical framework is discovered tomorrow? Or, more tangibly and perhaps inevitably, what happens the day a quantum computer becomes powerful enough to run Shor's algorithm and instantly unravel the discrete logarithm problem? Experts call it Q-Day. If the impenetrable racetrack of modular cryptography is suddenly broken and prime factorization takes seconds instead of millennia, how will human society completely rebuild digital trust from scratch? When the mathematical padlocks we've relied on for decades snap open all at once, what do we do next?
It is arguably the most pressing existential question in modern cybersecurity, a question of when, not if. The transition to post-quantum cryptography will be the greatest infrastructure challenge of our lifetime.
Exactly. Something to think about the next time you look at that little padlock icon in your web browser. Thank you for joining us on this incredibly dense, endlessly fascinating journey. Keep questioning the invisible systems around you. And remember, the next time you find yourself staring at the random numbers in your life, you aren't driving on an infinite highway. You're just doing laps on the racetrack. We'll see you next time on The Deep Dive.